Thank you. Am I audible nicely like this? Closer. Okay, good. Welcome. I'm so glad you're all here. We have a nice full room. I'm very happy with that. I'm going to tell you about self-supervised learning and take you on a journey through how that evolves while drawing some nice parallels to biology. As explained, I work at Sphere, which means that I'm regularly knee-deep in things like Python's Lightning, X-ray, scikit-learn, GeoPandas. And in addition to that, I like bouldering and I like bird watching. This is my newly crowned favorite bird, the red kite. Magnificent. And today the topic is vision. It's very important. We've got all these humanoid robots coming out nowadays. A new one every week seems the case. And these, of course, need to be able to interact with our world, right? They need to be able to exist in it, to perceive it, to reason about it. And it's also important for cars. They need to be able to see that I'm crossing the road like right in front of them, even though their light technically is green. And we, of course, like AGI. We're moving towards that, or so people say. And for that, we also need a way for it to perceive the world. But it's not a solved problem. We can see this from this example very nicely. This is a fake wall. You maybe saw this video, but I think it illustrates my point very well. If you were driving along the road and you'd see this, you'd brake. But a Tesla has more issues with that. A Tesla uses only a camera, so there's no real depth perception there. Vision is a hard problem, right? It's very difficult. It's tricky, but it's of vital importance. It's a basic requirement of interacting with the world. It's needed for AGI, which we're supposedly moving towards. So how do we as engineers, when we encounter this type of a hard problem, which is vital to solve, how do we tackle this? Well, for me, the answer usually is stealing, right? We find a place where the problem has been solved, and then we steal the solution. And I know, like, at least, I think 83 seats in this room, so 83, so times 2 places where this problem has been solved, and that's our eyes. They seem to be able to see quite well, and their brain seems to be able to process that quite well. So how does vision work in eyes? We have light entering through the lens, landing on our retina, which is then captured by a bunch of cells. We've got rods and cones. They react to various spectra of light. And this is then sent through this very nice nerve back to the back of our brain, right here, to the V1 visual cortex. This is where the image is received by your brain. And you can think of it like a screen. It's not really a screen, but it's also spatially laid out. There's measurements from the cells, so not really pixels, but you can think of it as a screen. It's then processed in this V1 area, which then recruits these sort of processing streams to give meaning to what you're seeing. From here, like pattern recognition starts, object detection starts, we start recognizing motion, we start recognizing places, these areas, these streams. They then recruit various different parts of your brain, so memory gets involved, feeling gets involved, until finally we achieve full understanding with all our humanness and consciousness of what we're seeing. And that's quite something, and we're trying to mimic that with computers, which is hard. So let's start with the first thing, which is replicating the basal processing, and only then we're gonna move on to reconstructing this meaning. So this basal processing, right? If we want to replicate that in computers, it might be nice to answer how is this done in the brain. And we find this out, like all great research, by prodding things into animals. In this case, cats. We ask a cat very nicely sedate it, and then we can stick electrode in its brain. And they're very small, and they actually hit like singular neurons back in the back of this cortex right here. We then ask the cat very nicely sedate him to look at these stimuli. These nice lines. There we show them several different lines, several different orientations, and we see how this neuron reacts. Before we show the stimulus, while we show the stimulus, and after we show the stimulus. We then do this for several different orientations, and we see that this particular neuron we've hit is very fond of purely vertical lines, which is good, right? This is a basic element of image which this neuron seems to like. So how does it do that? It probably has some kind of kernel or filter which it scans over the view in order to be able to see what is that? What's in order to be able to detect this thing it's like you're looking for, and that filter has been found in monkeys, because we had to get more animals involved, right? What we did is we again put a neuron in the monkey's brain to look for some activation, and then we showed the monkey similar stimuli, and we tried to fit a model that predicts the activations of the neurons we've hit. And as that model approaches an optimal fit, we can reasonably assume that this model is accurate to what the neurons are looking for. And then we find functions like this. So single dots, angled lines, fairly complex angled lines. And this is then what is done in this V1 area, and that then propagates to the rest of your brain until meaning is constructed. Can we do this in computers? Actually, yeah, quite easily. Oh, there's a slide. Take, for example, this very nice red kite. We split it up into several smaller bits, and then we tried to find 144 basal functions, which you can overlay, combine, multiply in various ways to try and reconstruct all these tiny patches of natural images. And then we find functions like this, which I'd say is quite similar to what we just saw. In fact, if we take this and we compare it to what an image classifier, even very quite simple ones like AlexNet, it's pretty old now, uses in the first few layers of its network, it's functions like this, it's kernels like this, which if we compare it to what the monkey uses, I think we're pretty much there, right? Basal processing, just from images to basic signals, I think that's good. We can do that. Meaning is a different story, right? It's harder. A very, very basic way to give meaning to something is through these classifiers. So if we simply show a model 1,000,000 images of 1,000 classes, and we ask it to predict what class do you think this belongs to, what class do you think this belongs to, and we keep going, we get a model which is able to recognize fairly nicely to which class an image belongs, which is nice and fun, but it doesn't quite capture the depth of the human experience, and it's not really scalable to new stimuli, right? If I show this model something new, it's just not going to be able to know what to do with it. And it doesn't really give us a usable end product. If I show you a dog, right, you recognize that it's a dog, but there's more in there. You know that it's a mammal, you know that it's related to a wolf, you might have associations with its color. There's a certain implicit understanding which you very quickly create or sort of dig up in your brain. And that's somehow what we want to find in the model. And this implicit understanding, this end product, which we can use for other things. I like to call it an embedding. Some people like to call it a feature or a feature vector. And it basically captures the implicit meaning into a vector of numbers, which is then usable for other tasks. This is quite an abstract concept, so let me illustrate this by a very nice example, which is called word2vec. Word2vec is a set of word embeddings, so it translates words, like we use and I use right now, into numbers. And we can then plot these numbers and attach the words back to them, and we obtain a landscape like this. If we zoom in a bit more, we see that words that are very similar, these are the roots of the word, so they might be missing some letters of the end, but citra and apple means citrus and apple. They're very close to tropic and melon, and right here we have beef and pork, which is close to seafood, which is closer to shellfish, to fish, than to pork. So there's a coherence here, right? There's understanding here, and you can imagine that we can then use these types of embeddings for things like sentiment analysis or even some basic analogy solving. If I take the embedding for the word king, I subtract the embedding for the word male, I add the embedding for the word female, I move to a space very close to queen, if everything is done nicely. So can we obtain something like this for vision? The answer is yes, because we want to replicate these streams, right? We need this meaning. A very early example of someone doing this is autoencoders. They've been around since around 2006. That was the earliest one I could find. And it's quite simple. We take any image, like purely randomly, this very nice red kite. We basically line up all the numbers, and then through a network we reduce the dimensionality drastically to obtain our embedding or feature or whatever you want to call it. We force this thing to have meaning by then also asking the model to re-extract the original image out of it. And it's going to be very bad at first, and it's going to be blurry, and it might be completely different, but as we keep training and training it, it slowly gets better and better. And by basically forcing the model to summarize this input to such an extreme extent, we generate some sort of meaning. That this works, I can show you with this face model, which is a bit later than 2006, but it's a very nice example. So these are the inputs. They are then fed through the autoencoder. They are reconstructed slightly differently, but I mean, there's definitely a resemblance there. But if we, before reconstruction, right, so at the point that we have this small embedding, if we add the embedding of the concept balding to it and then reconstruct the image, then we get into then we get into really fun stuff. Right? We can do some basic reasoning with this. I can also do the same for glasses. I can give them all glasses, and it kind of works. It's not perfect, but you can see that there's something here, right? We're getting somewhere. We're moving towards meaning. So an autoencoder gives us an extreme summary from which the inputs can be reconstructed, but there's no real understanding yet. We're still operating in this space where we can do something with it, but there's no sort of implicit meaning and reasoning completely there yet. So in our quest, I say we haven't finished, which means that we move on to the masked autoencoder, which is very similar to the previous one, except that we show it only part of an image. So we take out most of it and we say, okay, please create an embedding out of this, and then from that embedding, I want you to reconstruct the entire output, the entire input image. So even the parts which I did not show you. This is way more this is a lot harder than the original autoencoder, but it's way more powerful, right? Because you're asking the model to recognize what is in the image and then reason about the things which it cannot see. This works really quite well. As you can see from these two examples. So I really like this clock, because in the original you can see the beginning of this hand, right? And you can see that the short hand ends here. And our model has learned, oh, well then the long hand must extend. The same for this dog. There's no nose here, except that, I mean, we have ears and there's a bit of an eye. So the model very nicely predicts the entire perspective of the dog, where the nose should be. So there's actual, like, this goes way beyond image classification. This is thinking about the concepts. This is pattern recognition, and we're actually extracting way more meaning out of our data like this as well. So if we purely pre-train, we actually extract a lot more meaning from our images. So if we compare this masked autoencoding against just training normally on 1 million images, we obtain a way better accuracy score when we actually go to classify something. And we actually move well towards the accuracy score of a model which has been trained on 300 times the images. And the 300 times the images model also had actual labels for the classification, whereas our autoencoder just used the images. It just learned to predict where the nose of the dog is. So we're actually moving towards understanding here, right? If I see ears here, there must be eyes there. There has to be a nose underneath, etc. But there's one big problem here, I think, and that's that we're focusing on very unimportant noise. And a good example of that is this image of the zebra. So we're blocking out this big bit of the zebra here. And what we're actually doing is we're asking the model, so like this pixel specifically, what color is it? And the model doesn't really know. That kind of depends on the exact size of the zebra, how it's striped. And we can see that, right? It becomes this blurry mess. And to be honest, I don't really care what color it is. I just want the model to know that it's a zebra. You know that it's a zebra. So what if you focus purely on the meaning and not on the actual value of the pixels? We can do that through JEPA. This explanation is it's a bit complex, but stick with me for a moment. What we do here is we show a model part of an image. So say that it's divided up into 4x4 blocks. We only show it 2x3 of those. We obtain an embedding, and then we ask the model not to reconstruct the original input image, but I wanted to reconstruct the embedding of the original image. So I don't want it to say what color the pixel was. I wanted to think about the meaning of what was there, and then we compare it to what would have been there if we had shown it the entire image. What we're doing here is we're asking the model to reason about meaning instead of asking the model to reason about like the actual input pixels with all their real world noise and problems. To illustrate this a bit further, imagine I show you this, right? You know what bird this is. I've mentioned it multiple times by now. You know that it probably has an eye here, it has talons here, the wings go like that, the tail attaches somewhere here. But if I ask you, what's the color of this pixel? Like, just guess, what's the color of that pixel? You wouldn't know, and yet I don't dare to question your understanding of this image, even though I blocked out most of the actual interesting bit. And that's because you're smart, you can recognize it. And that's kind of what we're training JEPA to do. So with masked autoencoding, we're asking of this pixel, and with JEPA we're saying, okay, just tell me what you think what would have been there. And that really gets us somewhere, right? But we're missing one element here, in my opinion, and that's a time axis. Because right now we're looking at images, which is nice for understanding, but we want to move towards vision and reasoning and operating in the real world. And the real world, as you may have noticed, has a time axis, which is where video JEPA comes in, where we do basically the same thing, except that I block out a large part of a video and I ask it to predict what's going to be in that part this frame, what's going to be there this frame, what's going to be there this frame. And if you do this, it turns out that you obtain a model with very, very strong understanding and predicting qualities implicitly. Some people like to call this a world model. I'm not entirely sure what I think of that term. To illustrate this concept, imagine I show you a video of a bouncing ball, right? It comes across the stage like this, boing, boing, and then it goes into the covered part of the video. Well, you know what's going to happen, right? It's going to keep bouncing and eventually it's going to stop somewhere. By doing JEPA on videos, I'm basically asking models the same question. I'm asking them to predict what is going to happen in a very broad way. And that's super powerful. That way I'm giving it sort of an implicit understanding of the world, right? Just like you know that the ball's just going to keep bouncing and then eventually it's going to stop. If I ask you what happens when a car hits a building, you can tell me about that in great detail. First, the person driving is going to hit the brakes, right? The car's going to lunge forward. Eventually, metal's going to hit brick. Crumple zones start going. Chassis of the car hits the brick. Everything starts going down. And yet, you didn't have to like run a numerical simulation for this. You have this implicit understanding in your brain, and that's what we want to train the model by doing video JEPA. And that works quite well. If we look at modern video generation models, we can see very intricate play of the snow here, and there's been no particle simulation, there's been no equation set up, it's just implicit understanding of how our world works. And there's a little bit of errors. This, I don't know what like this bit of snow that's coming in here is doing. So it's not perfect yet, but we're getting there. And you can see how through methods like this, we're generating real-world understanding and reasoning capabilities. MU 3.5 is a really new model. It's been out like 2 months now, and it shows this very well. It's been trained on video, images, and text. So I can send it an image and say, "How can you please tell me how to make these Italian rissoles?" And it's like, yeah, of course. Like, you need these ingredients. It generates all these images. It generates all these steps. You can need these ingredients. You need to knead them together, shape them into balls, 6 of them, right? Fry them up, 6 of them. Plate them up, 6 of them. There's a consistency here. There's a storyline here. There's reasoning here. And that's what's enabled by doing this representation learning through time. This gets into why people call it a world model. Say that I show it this image of a living room, and with these like arrows, I'm saying I want you to move forward and to the right, while looking to the left and down. So we're basically sort of doing this motion, right? And then I say, okay, generate me the next image, which it does, and again, and again, and again, and we now have this model which is able to think about and reason and move in. It's not even a space, it's just an image that I showed it. And there's some slight inconsistencies. There's no flower here. There's definitely a flower there. And it also disappears again, right? So it's not perfect yet. But you can see that there's a sort of mindfulness here, there's an understanding here, which just isn't there if we're having like an AlexNet classifier, right? That's just able to say, oh, this is a dog. I think it's really cool. So this almost, I think we can say yes, right? We can mimic this processing, which is why right now, as we speak, you can go online and you can get yourself a humanoid robot. It costs 20,000 euros or 500 euros a month, and that robot is able to live in your house, charge itself, clean your countertops, do your dishes, do your laundry, do everything, right? The future is here. Except that if you wanted to do anything more complicated than like opening the front door very slowly, you need to call the company, you need to schedule an appointment for one of their employees to put on a VR headset to then remotely control your 20,000 euro robot to actually do the task, because we're not quite there yet. Granted, this is an ingenious way to collect so much training data, right? But this yes is kind of a lie. We can kind of do it, right? It's really cool, but we're not there yet. It would be cool if we get there. Not sure, but I'd like it, I think. Thanks for your attention.